Okay, let's run through the calculations for lab 5. We have a two-stage amplifier, stage 1, stage 2. They have all the same component values, so they're going to have the same DC operating point. Each circuit's going to have the same Z in, Z out, and AV. So if we solve for one circuit, we can just draw the same values one stage after another, put a signal on the input, attach a load, figure out how much we put in and how much we get out. And then here we are, we built it. It looks something like this. Okay, so let's start off with the DC analysis. So here's the schematic. We'll do one stage and that'll cover both stages. So the first thing you do in the DC analysis is you redraw the circuit with a single voltage source and a single resistor driving the base. So this voltage source would basically, so we're going to take these two resistors here and we're going to reduce them to a Thevenin equivalent. So detach it off of there, put those guys in parallel. VTH equals 20 times 33K, we're figuring out the voltage across this guy, over 133K. That is equal to 4.962 volts. 4.96 volts. The Thevenin resistance, basically detach the circuit, you short out your DC supplies, which would be here, which means that RB1 and RB2 are in parallel. So it's 100K parallel to 33K. That's 24.812 K ohms. Okay, now we have a circuit here, a voltage source and a resistor. That's creating base current. So now we want to solve for IB. And IB is going to be, it's a current, so we're looking for a voltage over a resistance. What voltage is in this loop here? I'd say this loop has, there's 4.96 volts. There's 0.7 volts. So the voltage is across the resistors in that circuit is 4.26 volts. 4.96 minus 0.7. So here's 4.96. We lose 0.7 there. These two resistors have the rest of it, which is 4.26. So that's the voltage. What's the resistance? Well, we got two resistors over here. This one here is the Thevenin resistance, so that's 24.8 K. And then we're going to add that to this resistance. And there's two things to remember about that resistor. This is basically the resistance on the emitter, which over here we can see is two resistors in series, so it's 480 ohms. But in order to solve for IB, what we want to do is we want to move that resistor over to the base side. So we need to multiply it by beta plus 1. (201 times 480 ohms. So basically we're going to move these guys over to the base side and we're going to multiply them by beta plus 1 to do that. Crunch, crunch, crunch. You end up with an IB of 35.1 microamps. Now did this extra 1, beta plus 1, make a lot of difference? No. Didn't make a significant difference. This is the exact method. I'll talk about that a little bit later. At this point, just keep the beta plus 1 in there. So IB is 35.1 microamps. Now we can solve for IC. It's going to be beta times IB, which is going to be 7.03 milliamps. And IE is going to be beta plus 1. It's a little bit bigger. It's going to be 7.06 milliamps. So essentially IE is going to be, it's the biggest one. It's the sum of those two. Okay, so I figured all the currents. Now, so from that we can figure out the voltage across the resistor. So here's VCE. Basically we started with 20 and we lose voltages across these three resistors. Then whatever is left is the voltage across the transistor. So voltage across the transistor is going to be VCC minus ICRC. ICRC is basically the voltage across this guy minus IERE, and this is both REs. So 20 minus 7.03 milliamps times 1.5 k ohms minus 7.06 milliamps times 480 ohms. Calculate those out, you end up with an IC, 7.03 milliamps. So here's VCE. Let's just draw a quick curve. Actually, you crunch this out, you end up with 6.067 volts, to be precise. So there's the numbers we got so far. Let's draw our load line between 20 volts, that's the cutoff voltage. VC off, IC sat would be 20 volts over 1980. That's about 10 milliamps. The operating point is 6 volts, someplace about there. And 7 milliamps, about 70% of the way up. There's our Q point. We're operating someplace in the middle of the load line. We're ready to amplify a signal.